Today's lesson will be about quantum mechanics, just very simple introductory quantum mechanics. I'm not going to really focus too much on the theory. I'm probably going to talk fast. Uh, I'm going to strongly recommend that you read through chapter 12.1 and 12.2. There's going to be a lot of theory that I'm not really going to dive deep into. I'm going to try to focus on walking you through a little bit of the math for some of the things that you're going to be expected to do on the next quiz. So if you want a quite a bit different version of these notes, because I trimmed a lot of stuff out of them, please go to May 28th and you can download a version of these notes. If you want a little bit more background reading, you can read this website, chemistryland.com. They kind of broke it down and went as far as atomic theory and obviously related a lot of the stuff to chemistry. And if you want just kind of an introduction to quantum mechanics, in fact, I'm going to strongly recommend that you kind of pause this video right now, and down below there'll be a link in the descriptions for Physics Girl. She kind of introduces you the topic of quantum mechanics very nicely, much higher production quality than this is ever going to be. So I'm going to assume that you will watch this as I move forward with this video. All right, so there was a lot of question about what light is, and then around Newton's time. So there's stuff going on before Newton, but I'm just going to start with Newton as some place to start. Newton kind of made the declaration that light is a particle. He did some work with optics. Obviously, he's got his laws of motion, his universal gravitation, made calculus. He was a pretty smart guy. And if he says that light is probably particles, a lot of the scientific community just more or less shrugged their shoulders and said, yeah, you're probably right. There was obviously some people who thought otherwise and tried to prove him wrong. And, you know, they had their own ideas. I'm going to skip over all of them and go up another 100 and so many years to the late 1700s and early 1800s, to when a man here by the name of Thomas Young and a few other people, but we'll just focus on him, finally devised an experiment to prove one way or the other whether or not light was a particle or light was a wave. And so the idea is particles cannot interfere with other particles. They have collisions, they transfer momentum, and therefore cannot have an interference pattern. So what Thomas Young decided to do is pass monochromatic light, so that means coherent light, light of only one wavelength, through a double slit. So kind of like what you've seen probably in grade 11 with the double slit experiment with water even, and it creates this interference pattern where you have a bunch of constructive and destructive interference. You end up with nodal lines where the water will be perfectly still. And so that is the base idea of an interference pattern. Okay, so if light is a particle, then this is probably not going to be seen. So he ran the double slit experiment. Light passed through two slits. Obviously didn't see this part because this is just sort of the example that you'd see with water. But if you remember, you'd have that interference pattern here that you'd look down from the top. If you're looking at a water tank, that is what you'd see. But what he did is he had to push the light onto a screen so that he can actually see those interference patterns. And what he got was a series of bright and dark lines. So all the bright lines represented constructive interference, all the dark lines represented destructive interference. So those would be the nodes. And so this was pretty conclusive evidence that Newton is wrong. Light is not a particle, light is a wave. And we did look at waves, light as a wave in grade 11 quite a bit. In fact, that is what we focused on in grade 11, the wave version of light. And that is very true still to this day. Light has wave patterns. But back in the 1800s, this was kind of conclusive evidence that, well, there's no way light can be a particle. Light has to be a wave. And that's very good and all, right? So with particles, we know that if you try to do that experiment with particles, all right, so you can even blow that up to macroscopic, our size, right? If we get back into my classroom, and if we throw a bunch of balls, tennis balls, footballs, basketballs, whatever we got in the room, ping pong balls, through both of my doors in my classroom, we're going to really annoy Mr. Link with the balls that hit the lockers outside of his room there. We'll probably annoy Mrs. Hamilton with the balls that would hit outside of her room there. All right, so that's all we do though. There wouldn't be any interference pattern where some are up here and some are down there. All right, we'd only hit the lockers that are just outside Mr. Link's room and just outside Mrs. Hamilton's room. Right? That's how the macroscopic would work. There's no way particles can suddenly just do an interference pattern where we have a nice set of patterns on the locker doors outside of my classroom. So To summarize, which I'll use this slide from the Institute of Quantum Computing. If you actually have interest in quantum mechanics, you're probably going to get ready to move to Waterloo. Very nice place. These guys are great at what they do. Anyways, so what we know about particles, we know particles are localized, right? They only exist in one place at one time, right? If you're playing a game of basketball, there's only one ball on the court. It is localized. Sure, the ball is moving, but it is can only be in one spot. Waves, on the other hand, they're delocalized. If you jump in the pool, that wave is spread out across the entire pool. If you jump into the lake, the wave will spread out throughout the entire lake. Obviously, it's going to lose a lot of energy and pretty much fizzle out. But if we talk about that perfect world where there is no energy lost and no friction, then yes, that wave would spread out throughout the entire lake. It's a bit more obvious with swimming pools because they're a bit smaller. Right? Particles have a definite mass and volume, whereas waves don't. Waves have to be looked at through their wavelength and their frequency. Some people would argue that, okay, well, what about water waves? Water waves require water. I was like, all right, fair enough. Like, well, water has mass, so therefore a wave has mass. No, it doesn't. The water itself is still a particle. So a wave can travel through a medium, so whether it be water, whether it be the ground, or it doesn't need a medium whatsoever, and that is your electromagnetic radiation. So you don't actually need a medium for a wave to travel through. So right away, that truncates that. Waves do not have mass and volume. Only particles do. And when particles interact with other particles, they have collisions. So you can look at your conservation of momentum, your conservation of kinetic energy, determine whether it's elastic collision or inelastic collision. So particles, we can transfer the energy and figure out where that energy has gone. Waves, on the other hand, they do not have collisions. They do not bounce off each other. So lightsabers cannot happen. At least not with today's technology, and I don't think with tomorrow's technology. So lightsabers, if they were truly made out of light, they would just go through each other. And so you cannot have collisions with light if light is a wave, because waves just go through each other. Right? And particles are countable, right? You just think of a pack of Skittles, you can count every single individual Skittle. If I have a package of Skittles and you want some Skittles, you ask nicely and then I'll give you some Skittles, but at the slowest rate I can deliver them to you is going to be one Skittle at a time. I could give you a handful at a time, but at the very minimal, I can only give them to you by one little particle, if you will, at a time. So think of that as the smallest amount possible, okay? Waves would be continuous, right? It would just be a constant transfer of energy, if you will. So with that defined as is, in the late 1800s, early 1900s, they were having the whole ultraviolet catastrophe and a bunch of other things. And physicists sort of noticed that if you shone light of very specific frequencies on certain types of metals, that light would actually eject electrons. And the electrons that got ejected, they called photoelectrons, because it was light that actually kicked the electrons out. If light's a wave, that shouldn't happen. Right? So waves cannot kick electrons out. Waves cannot force out particles. So that must mean this is clear evidence that, oh, okay, well, maybe light is a particle. Maybe Newton was right after all. It's like, well, what about all that evidence from Thomas Young and other evidence that they've just gathered since then? So there was a bit of a confusion for a while there as to what exactly is going on. Einstein kind of took Max Planck's work and sort of made this make sense for people. He said, well, of course, this light is going to kick out this energy, or this electron, because light itself has energy based on the frequency. And Max Planck said that the lowest type form of energy possible is, of course, his constant, 6.63 times 10 to the negative 34 joules per hertz, otherwise known as joule seconds, right? That is the smallest parcel of energy that can be delivered. And that little parcel of energy is known as quanta, so quantum mechanics. So he devised that whole notion that, okay, the energy of that incoming light must have delivered enough energy when it interacted with that electron to kick it out. And if that frequency does not have enough energy, if that little wave does not have enough energy, then nothing will happen. And so that's what you kind of see here with this red light. The energy is low and therefore it does not possess enough energy to kick out one of these electrons. The green light has enough energy, therefore it kicks out an electron. Blue has more energy than green. So if green can kick out an electron, so can blue. And since blue would have more energy, blue light would have more energy, 400 nanometers, the electron will be kicked out with a greater amount of kinetic energy. It goes out with a faster speed and therefore more kinetic energy. So this light was giving kinetic energy to these electrons. That can only happen if light is a particle and therefore possibly possesses momentum. We'll get to that in a moment. So photons have two important properties. Photons do not have mass. Particles were said must have mass, otherwise it's not a particle. Photons are obviously an exception to that, right? Photons can also exhibit interference patterns, which is more of a characteristic of a wave. So in other words, photons have both wave and particle properties, and therefore light, which is where our photons come from, have a wave-particle duality. It is both a wave and a particle, yet neither at the same time. Light is its own thing. Its properties are dependent on the situation. So that's one way to look at it. So back to this equation for the photoelectric effect. So the energy of incident light colliding with this metal to kick out these photoelectrons. I know I said this out loud, but here it is. So Planck's constant is 6.63 times 10 to the negative 34 joules seconds, technically joules per hertz, but the inverse for hertz is a second. But if you use the electron volt, which often a lot of people who work with quantum mechanics use electron volts instead, you would just take this value divided by 1.602 times 10 to the negative 19 joules for every electron volt, and you'd have an equivalent version in terms of electron volts, 4.14 times 10 to the negative 15 electron volts a second. Okay. If you're looking up quantum mechanics across the internet or in other textbooks, you might see, instead of it written down, the photoelectric effect written down as HF, you might see it written down as H, and it does look like a V. This does look like a V, but it's the Greek letter nu. It's kind of like a fancy V, if you will. I've seen it written many different ways. Sometimes I see it written like this. That's kind of horrible. I can't draw with a mouse. But it's just a different letter altogether. I'm not sure why they use the Greek letter nu. I'm sure there's a reason to it. I never did discover what that reason was. But for grade 12 and probably your first year university, if you have to do this again, it'll probably be F, and that's good enough for us. So they determined that obviously there must be a minimum amount of energy required to kick out these electrons. And so at the time, electricity was starting to become very well known across all of the world. Right? Some people, especially where we grew up in Saskatchewan, Alberta, you go back to 1900s, maybe your parents, great-grandparents didn't have electricity in their homesteads, but electricity was pretty much widespread throughout the world at this point. And so scientists were pretty good at figuring out ways of manipulating electricity. And they were able to determine that if you actually take a metal sample, we can figure out how much energy must be required to physically remove electrons from this metal sample and have them pass over a vacuum and hit a different metal plate. So we call this minimum amount of energy that would have to be introduced to this sample as the work function, where they would just vary the voltage, electric potential between the two plates. And once it got to that minimum amount of voltage, maybe 1 volt, 2 volts, 2.3, you get the idea. You would just say, okay, well, that's what the electric potential difference needed to be to kick an electron out. Well, then you would just say your work is equal to the electron, E, multiply by whatever the voltage is, right? So if it was 5 volts, then you'd end up with your work functions equal to 5 electron volts. Or of course you can convert into joules by just saying, okay, 5 volts times the 1.602 times 10 negative 19 coulombs for your actual electric charge. So that is mainly why physicists like to use the electron volt, because we have a way of directly comparing it to physically removing these electrons. Never mind shining a light onto the sample. We can physically do it by applying a voltage, electric potential difference between those two. Why light was able to do that? They were dumbfounded by it. They had no idea. They found it quite confusing. So some experiments were made, and they found out, okay, well, there has to be a minimum amount. So of course they found the threshold. They found the the work function for all sorts of different metals, and they worked this equation backwards. So the equation for the incident light energy. Instead of it being E for energy, they just said, okay, we'll make that equal to the work function, and we'll solve for that minimum frequency necessary to kick the electrons out using light, not by actually using electricity. Just using light, work the equation backwards, find out that minimum frequency. They call that minimum frequency the threshold frequency. And then they actually found by varying different metals, grabbing a whole bunch of different metals, therefore they would have different threshold frequencies. And as they ran more and more and more experiments with many different frequencies, they found that there was a pattern. As you increase the frequency, so increase the type of light, anywhere from infrared to ultraviolet to X-rays, the electrons would leave as the energy of the electromagnetic radiation got higher and higher and higher. The photoelectrons would leave with more and more and more kinetic energy. And so they found that there was a lovely linear relationship with the amount of incoming light hitting the metal plate and the energy of the photoelectron that was ejected. So if we actually plot that, you'd get yourself a linear relationship where the slope of the line of this linear relationship is actually Planck's constant. The x-intercept would be your threshold frequency, and your y-intercept, well, that is the energy of your work function. And of course, your work function would vary depending on the type of metal that you are using. And so we ended up with the equation, the kinetic energy of your photoelectrons that are being ejected out are equal to the incident energy of the light that comes in, so that's very dependent on what the frequency is, minus your work function. And it looks like that. That is your y is equal to m, so that's your Planck's constant, x, that's your frequency, plus b. Well, in this case, we know we're below the x-axis, so that plus b is technically a negative w. So that means if your frequency if your incoming light, frequency times Planck's constant, is less than your work function, you're going to get a negative kinetic energy. And since you can't have a negative kinetic energy, that means no photoelectrons are being ejected. All right, so this energy of the incoming light has to be greater than or equal to, well, slightly greater than the actual work function before any electrons are being kicked out. All right, so this is the equation we're going to use for the kinetic energy of our photoelectrons. So this is actually what Einstein got his Nobel Prize for. Now again, if you look this stuff up online, you'll probably see this symbol depending on the websites you look at. If you're looking at high school websites, for the most part, they use F in high school and W in high school. Once you get further along into the quantum world in university, they'll start changing out W for, my brain is dead for a moment, phi, and they tend to use nu for frequency. Not sure why, it's just the way they did it. So don't be afraid if you see the work function look like this. We're going to stick with this, the nice simple letters. So now there's a little bit of the theory. That's a lot of the stuff that physics girl didn't get into. She doesn't really get into the math, and that's fine. We don't need her to. So that's basically where the math comes from. You're basically doing the slope of a line. So let's do a quick problem. Aluminum is being used in a photoelectric effect experiment. The work function for aluminum is 6.73 times 10 to the negative 19 joules. Calculate the minimum photon energy and frequency needed to emit electrons. Well, minimum photon energy is given in the question, 6.73 times 10 to the negative 19 joules. Don't know who wrote this question, I just copy and pasted it in. So really we're just looking for the frequency of the emitted electrons. Part B gives us light, ultraviolet light of a certain wavelength, and we're to determine what the actual kinetic energy is of the photoelectrons. So shrink that down so I have more space. My work function given to me is right there in front of you. Right? I need to find the minimum energy. Again, it was given to us, so that's how much energy is needed to kick a photoelectron out. I'm going to just convert it into an electron volt, only just so that you see it done. So if I divide this by 1.602 times 10 to the negative 19 joules for every electron volt, that's how you get it into electron volt format. And for the most part, this is kind of why physicists like the electron volt. Very often it gets rid of this scientific notation, right? And this is a much easier to look at than obviously that. But for the most part, we're still technically relating a lot of this stuff to classical mechanics, and for that we like to use the joule. So to find the threshold frequency, we'll just take the work function, make that equal to Planck's constant times the threshold frequency, F naught. Manipulate the equation, and then just plug some numbers in. All right, so I won't spend too much time on that. If you take Planck, the work function of aluminum divided by Planck's constant, you should get to 3 sig figs, 1.51 times 10 to the 15 hertz. So that's a pretty high frequency. To part B, you're not given a frequency, you're given a wavelength. So a wavelength of ultraviolet light. So that wavelength collides with the metal plate of aluminum, and we're to determine whether or not electrons are actually emitted. So if we can solve for a positive value of our kinetic energy, then obviously electrons are emitted. From grade 11, the universal wave equation said the speed of any wave is equal to wavelength times frequency. Since we're talking about ultraviolet light, we know what the speed is. The speed is the speed of light. We assume it's in a vacuum. There's a big thing that you have to kind of just always assume you're in a vacuum, or at the very least assume you're in air. And the value for C in air is pretty close to the same thing as it is in vacuum. So you can interchange those for the most part, especially at the fundamental level. When you get into the higher end level of quantum mechanics, you'll probably need the long 9-digit value of light. So manipulate the equation to solve for frequency. If you want, you can plug numbers in at this stage and find out whether or not this value of F is greater than the threshold frequency. If it is, then electrons are kicked out. If F is smaller than the threshold frequency, then obviously electrons won't be kicked out. But I'm not going to. I'm just going to plug it into the equation, replace it, F in this equation with speed of light over the wavelength, because often I'll also see this in a lot of work. And then you just plug numbers through, plug and play, just like you've been doing all semester long. Cross off the units as necessary, work it through. So I showed this intermittent step because my energy of the incident light of wavelength 125 nanometers ends up being 1.59 times 10 to the negative 18 joules. So definitely larger than the 6.73 times 10 to the negative 19 joules. So we are going to get an electron being kicked out. So I took it one step further. I added a significant figure just so I have 3 in the end. I like having 3 sig figs in the end. And you end up with 9.18 times 10 to the negative 18 joules. If I converted that into the electron volt, I'd basically just divide by this up here, and I'd end up with 5.73 electron volts as its kinetic energy. Okay. I could find out how fast it's going. So before I do that, just kind of remind you, for your electric potential, that's your voltage, capital V for voltage, lowercase v for velocity. If we wanted to find how fast the electrons are going, we would just make that equal to 1/2 mass times your velocity square. Now this, of course, is assuming that these electrons are not traveling with relativistic speeds. Remember, once you get to about 10% of the speed of light, so roughly somewhere around 3 times 10 to the 7, then you should probably replace this equation with your special relativity equation for your kinetic energy. But if it's going slower than that, then this is a good enough approximation. I'm not going to find the speed. The question didn't ask for the speed, but that's just something that you'll probably see in the future. So you'll also see in some of your questions something about stopping voltage. So stopping voltage is a kind of a way of directly measuring the kinetic energy without, I know I said earlier in the semester that you can't really measure energy, but we can measure voltage. So voltage is the amount of energy that a charge has as it passes through 2 points. So what Robert Millikan has done, so to give some props to whoever did this, he grabbed 2 plates. One was positive, one was negative, cathode and anode respectively, and he shone some light on it that was high enough to actually kick out electrons. And so those electrons were kicked out and they had a certain velocity. Now, because those electrons had motion, they had velocity, they were colliding with this negative plate. I realized the fundamental law of charges say like charges don't like each other. However, they had enough velocity, they would strike this plate and they would create a current, right? So you can actually measure the current that these guys were producing. So what he did is he hooked up a circuit to it and he just reversed the polarity of the battery, if you will, to the point where this would become increasingly more negative as he turned up the voltage. And what would happen is, with this incoming light hitting this plate here, electrons would go so far and he'd find that fewer and fewer strike this plate, up until the point where once this plate became a much higher negative value, it became so negative that obviously these things would stop striking the plate. The moment these photoelectrons stopped striking the plate, he no longer was able to measure current. And at the point where you cannot measure current, you have matched the kinetic energy of these photoelectrons. Once you've matched the kinetic energy of these photoelectrons, you now have a way of measuring the kinetic energy of electrons. So obviously, we'd have to just make it negative to get the equivalent value, because that's kind of what we're doing. So we just take the reverse value. So if this was, say, took -5 volts to stop this electron from hitting this plate, then we'd just say, okay, well then we'd call it 5 volts, positive 5 volts necessary. 5 electron volts were necessary to stop this electron from striking that plate. And so we have a way now of directly measuring the kinetic energy. And the equation would be the charge of the electron multiplied by whatever that stopping voltage was. Sorry, that took a little long to get through. All right, so the stopping voltage in a certain photoelectric effect experiment is 10 volts, and the incident wavelength of the light source is 105 nanometers. So again, we're in the ultraviolet range. What is the work function of the metal surface? So in other words, using the equation for Einstein's kinetic energy relating to the incoming light of the photon and the work function of the metal plate, we're looking for the work function. So it's just a matter of replacing the kinetic energy of the electron to the stopping voltage multiplied by the charge of the electron, and you just do a quick little equation manipulation to solve for the work function. We weren't given frequency, we were given the wavelength, so we would just use the appropriate equation, replace frequency with c over lambda, and you would literally just plug everything in. All right, so I won't spend too much time on that. You can pause the video if you need to see it. But at this point, oh, I should probably point out, when we do this conversion with 10 volts, if we're going to keep it in joules, volt is a joule per coulomb. So when you multiply by the charge of an electron, the coulombs will cancel out, and you should be left with a joule in the end. So work the numbers through. You'll end up with the work function to be about 2.9 times 10⁻19 joules. Now that's enough information to more or less get a good estimate of what that metal actually is. You can go to Wikipedia and just look this up on a chart, and it should be fairly close to something on Wikipedia. It might match with two things. I forget, to be honest. If we did this experiment, if we did this question with electron volts, I would have taken this value that I got in this step right here, the 1.89 times 10 to the negative 18 joules. I would have divided it by the 1.602 times 10 to the negative 19 joules for every electron volt. So in other words, convert this into electron volts. And when it comes to, that's where I got the 11.8 electron volts. When it comes to the 10 volts for the stopping voltage, all I'd have to do is just tack an E onto that, because we're talking about the energy of a single electron. So I could just call it 10 electron volts. So that's a lovely conversion right there. Basically, we just don't take the charge of the electron in its numerical form. We just leave it as E. And again, that is one of the reasons why the electron volt is so handy. So you got two different options. Sometimes you'll get the answers in the back of this book in joules. Sometimes they'll be in electron volts. So last little bit, I realize this is getting long, I'm very sorry. Light ejecting photoelectrons implies a collision. So I've mentioned that once or twice, and therefore that implies that light has momentum. But light does not have mass. Photons do not have mass. So how does this work? So remember, your momentum is equal to your mass times your velocity. So I replace the V with C because we're talking about light. Obviously, light does not have mass, so we've got to kind of get around that. So the way to get around that is to combine that with special relativity. So Einstein showed that energy and mass are pretty much one and the same thing. It is a mass-energy equivalence, and therefore we were able to take the equation for rest mass, rest energy, manipulate it for the mass, and then you can therefore plug that into the momentum equation. And now you've gotten a way of measuring the momentum of light, because light does have energy, right? Energy is part of the electromagnetic radiation, and obviously it would have to have energy. We can plug that in place of mass, and we have a way of getting around the whole notion that light doesn't have mass. We now have an equation for momentum. And since we're talking about light, and Einstein gave us an equation, a lovely equation for the photoelectric effect, which would be Planck's constant times the frequency, we can just replace this energy with HF, as you see down here. And then you end up with a couple of different constants, Planck's constant and the speed of light. So if we actually replace frequency divided by the speed of light, we can get an equation with your wavelength. So that is done by the substitution of universal wave equation, whereas frequency is your speed of light divided by your wavelength. If you put this into the equation for the incident energy of the photon, your speed of lights cancel out, and you are left with the equation of the momentum of a photon with respect to its wavelength. All right, and that is a popular one to use when you're calculating the momentum. So if you know what the wavelength of light is, you can figure out what its momentum is with just one quick little division. So this is the last one we're going to work on, and then I'll stop this video because we're at that 30-minute mark. So suppose an atomic nucleus at rest emits a gamma ray with energy 140 kiloelectron volts. Calculate the momentum and the wavelength of this gamma ray. So if you remember from grade 11, gamma rays are very high energy, very dangerous. They can pretty much destroy DNA, so you don't really want to be around gamma rays. So first of all, let's calculate the momentum. The momentum is the energy divided by the speed of light. So if we convert this 140,000, remember kilo is 1,000 electron volts, we'll have to do the conversion, 1.602 times 10 to the negative 19 joules per electron volt. So we do a multiplication this time. We're going from electron volt back to joules, then just divide by the speed of light. And you should end up with a value 7.48 times 10 to the negative 23 kilogram meters per second. So there's your momentum. If you were an actual quantum physicist, you would just say the momentum is just 140 kiloelectron volts per speed of light, right? Because very often in quantum mechanics, they treat the speed of light as a unit because people can easily just put the number in place of that, but it's so much easier just to say, okay, if it's got an energy of 140 kiloelectron volts, then it would have to have a momentum of 140 kiloelectron volts per c. So again, I've mentioned this in a previous video. It's a lot handier to remember this way. And we can say that, yeah, I'll stop there. Moving forward, to find the wavelength of the photon, of this gamma ray, we would just take that, we could have just taken the energy, but we're going to use the momentum equation and just manipulate it so that we can solve for our momentum. So we just, solve for our wavelengths. We just do a game of switcheroo, switch places with the momentum of the photon with the actual wavelength of the gamma ray. You end up with that relationship, a ratio of the Planck's constant over momentum, and it's just a matter of plugging in the numbers. Okay, remember your joule is a kilogram meter square per second square. If you multiply by a second, you end up with a kilogram meter square per second. And so everything will cancel out except for the meter. In that case, you end up with 8.87 times 10 to the negative 12, or 8.87 picometers if you use your metric prefixes. So smaller than the nucleus of an atom. That was a lot of information all at once. I realize I focused mainly on the math. I definitely skipped over a lot of theory, but that is just some of the mechanical parts of quantum physics, stuff that they were trying to figure out in the early 1900s and up to about 1920. When they had some other issues with quantum physics, but I'll save that for a different video, and I'm going to strongly again recommend that you do read some of this information and email me if you have questions. All right, thanks for watching.